Welcome students. Myself Dr. Monika Khetarpal. I welcome you all in the lecture series of MSc Final Physics. We were dealing with the fifth paper and we were discussing antiferromagnetism. First of all, I am giving you a brief review what I taught you in my last lecture. Antiferromagnetic materials are those materials which have equal number of opposite spins. If we divide a ferromagnetic material into two sublattice, then in one sublattice spin will be parallel and in another sublattice there are equal number of opposite spin. We will discuss the molecular field theory of antiferromagnetic material. We are dividing our material into two sublattices which are denoted by capital A and capital B. And as we have discussed in our last lecture, we have determined the molecular field at A and B sublattice and assumed the molecular field at A and B sublattice to be HMA and HMB. Here H is the external applied field. The parameter minus alpha determines the interaction between same type of sublattice. That is, it describes AA interaction and BB interaction. And minus beta denotes the interaction between adjacent two sublattice. That is, it describes AB interaction. Here Ma and Mb denotes the magnetization of A and B sublattice. Since when we are considering A sublattice, then the field at A lattice will be HMA will be equal to external field, and on A sublattice there is an interaction of A with A which has a parameter minus alpha and the field is Ma, and since A also interacts with B sublattice through an antiferromagnetic interaction which has a parameter minus beta, so the value will be minus beta Mb. Similar is for HMB. We have obtained these two values of field at A and B sublattice, and we have also considered in our last lecture the temperature range T greater than Tn. Here Tn is the Néel temperature. Now in our today's lecture we are going to discuss the temperature range T equal to Tn. Along with this, we have determined the formula for susceptibility for an antiferromagnetic material to be equal to chi equal to C upon T plus theta. The constant C is Curie constant and it has a value 2 nu square upon 3 kb, and theta is n mu square alpha plus beta upon 3 kb, and when it is expressed in terms of Curie constant, it is half C alpha plus beta. Now I am considering the range T equal to Tn. Since the temperature is Néel temperature, so we have a condition in which there is no external applied field. That means in this condition H will be 0. So I am substituting H to be 0 in the expression. First, this H is equal to 0. On substituting H to be 0, I get Ma to be n mu square upon 3 kBt Ha. Substituting the value of Ha, I get my Ma to be equal to minus n mu square upon 3 kBt alpha Ma plus beta Mb. This is the value of magnetization at field at sublattice A. Now I am collecting the terms which have a factor Ma. Similarly, I will solve for Mb. So I get these two expressions, and these two equations will have a solution of Ma and Mb if the coefficient of the determinant of the coefficient vanishes. So forming the determinant of Ma and Mb from these two expressions, and as I have already stated that constant C is equal to 2n mu square upon 3b, I am expressing my determinant in terms of Curie constant C, and here we have used T to be equal to Tn. Solving the determinant, we can get the expression of Néel temperature, and on solving I get my Néel temperature to be equal to C upon 2 beta minus alpha. This is our Néel temperature, and this shows that Tn will increase as the antiferromagnetic interaction beta becomes stronger. That means Néel temperature rises with the AB interaction, and this Néel temperature decreases with the parameter alpha. Now this is the value of Tn. I am obtaining a relation between Néel temperature and a constant temperature denoted by theta. We have find susceptibility to be equal to C upon T plus theta. This was the value of theta, half C alpha plus theta. Now using this theta to be equal to half C alpha plus beta, and my Tn is C by 2 beta minus alpha. I am dividing both the expression, and this is the relation between Tn and theta, that the ratio of Tn to theta is equal to the ratio of beta minus alpha to beta plus alpha. So I have two temperature range. The first temperature was above the Néel temperature, and second was at the Néel temperature. Now I am considering the third temperature range, which is below the Néel temperature. In this case, I am going to find the susceptibility, and I am taking the two conditions, and the two conditions are: suppose I am applying the field perpendicular to the axis of spin, and in the second case the field applied will be parallel to the axis of spin. So taking the first condition initially, that is the external field is applied perpendicular to the axis of spin. I have two sublattices which are denoted by A and B, and we are applying the field perpendicular to the spin direction of these two sublattices. This is my lattice A spin direction, and this is my lattice B spin direction, and the field is applied perpendicular to these direction. Here I am assuming that only interaction is AA and BB. That means, sorry, I am assuming for simplicity that the interaction is only AB. We are ignoring the interaction AA and BB. Now I am applying the magnetic field. This is the direction of my initially spins. That means initially spins are in Z direction. This is the direction of plus Z denotes the direction of A sublattice, and the direction of B sublattice is minus Z. And we are applying external magnetic field in the perpendicular direction. This is the direction perpendicular to the Z direction, that is X direction, and in this direction we are applying the external magnetic field denoted by H. Now, by applying the field, these dipoles will make a certain angle phi with the original direction because they tend to align themselves in the applied field direction. The directions that dipole make with the initial direction, let it be phi. Now I am going to find the effective field in both directions, that is Z direction and X direction. For this purpose, I am assuming that the effective field of spin in the Z direction to be equal to Hz plus minus beta m0. Here m0 denotes the magnetization initially without the application of external magnetic field. And similarly, in the X direction, the field Hx will be equal to H minus beta delta m. Because we have applied the field along x-axis, so there is an additional term which is equal to H in this direction, and the change in magnetization is also along delta m is also along x direction. This delta m denotes the change in the magnetization. So the ratio of change in magnetization to the original magnetization, that means delta m upon m0, this will be equal to hx upon hz, and substituting the value of hx and hz, I get this to be equal to delta m upon m0. This is equal to h upon beta m0 minus delta m upon m0. From here on solving, I get my susceptibility in the perpendicular direction chi denoted by chi perpendicular to be equal to 2 delta m upon h, which is equal to 1 upon beta. As the total magnetization is equal to 2m and susceptibility equals magnetization upon strength of magnetic field, and it is equal to 1 upon beta. And from here we can say that at the Néel temperature the susceptibility is constant as beta is constant. Now I am considering the case in which I am applying the field along the direction of spin. When we apply magnetic field along the direction of spin, then in this case there is no change in magnetic energy because there is no variation in spin alignments. Hence, on applying a field parallel to the direction of spin, chi parallel, the susceptibility is 0. This is the condition at T equal to 0. But as the temperature increases, chi parallel also increases. So, we have discussed the three temperature ranges of a ferromagnetic material. Thanks a lot for watching.